All right, let's talk now a little bit about how the stars form. So we learned about where they are formed. They are formed in relatively dense molecular clouds, like this one, which, thanks to the gravity pushing in all direction, will collapse and fragment, and each of the fragments will become, we called it a star, but it's not really a star, it's a protostar, almost a star. During the process, we have the conservation of energy and angular momentum, which heats up the core, so it's very hot, because the whole fragment of the cloud of gas loses the potential energy, which converts into kinetic energy that makes the temperature go up, and then it becomes a disk. So cloud flattens thanks to the conservation of angular momentum. So this is thanks to the conservation of angular momentum. It's very hot in the core thanks to the conservation of energy. All right, and that's disk of gas, the flattened now gas around the very hot protostar. It's going to be spinning faster and faster and faster. Sometimes in the very late stages of the collapse, the central protostar may actually fire jets, highly collimated jets of matter, again thanks to the conservation of angular momentum, and those jets happen along of gas happen along the rotation axis. Okay, so protostars rotate rapidly, and some may spin actually so fast that they split to form close binary star systems. And we talked about binary star systems. They play a really important role in helping us actually get the masses of stars, because otherwise we would not have any good idea of how much matter is in the stars. A few words about what happens during this formation of the protostar. How do we actually know about this? What kind of observations do we use to get these ideas that the process follows these phases? As the cloud collapses, as we said, the gravitational energy is released and tries to heat up the gas because it's converted into kinetic energy. In that process, the central gas, the central thing that becomes now the protostar, needs to actually get rid of its heat so that the cloud remains cool and keep collapsing, right? So in order for this to remain cool so that it doesn't push against gravity, okay, to continue the collapse, will emit some radiation, infrared and radio light. And that's how it cools down. And this continues until the cloud gets too dense and opaque to the radio and the infrared cannot escape. Okay, so here the star or the protostar becomes opaque to infrared and radio. So that's it. This is when actually the protostar is formed, because there is no more collapsing under gravity, and even though it's powered by gravity, all of that emission that we see during this process all the radiation, all the light that we see. It's light, right? So it's the photons. They're powered, all emission is powered by gravity, okay? And it's going to do that. This gravity, the push inward of the gravity, is going to happen until the protostar becomes opaque to infrared and the radio. And that's when the protostar, that's when the protostar is basically is becoming hot enough for eventually the fusion, the process of fusion of hydrogen into helium will start. And we're going to talk about that in a second. Show to you some example like how that growth and the stop of the growing process of a protostar happens. So here's an example of gas that's driven by young stars which are outside the image area, so kind of like here. So this is a nearby young hot star which is blowing some winds. Bright young stars outside are blowing gas past it, and they're as a consequence they're going to strip away gas that has not yet fallen onto the new star. And as you can see, this newly formed star, this would be the protostar, or the newly formed star, maybe a protostar still, blocks the flowing gas like a rock in a stream. And you see, as a result, the flowing gas forms a structure around the star that's similar to the wake of a boat, right? You see that? Pretty neat, right? Okay, so it's events like this that help this collapsing of just adding basically of material onto that protostar. So how do we get from the protostar to the real star, right? The shining or living main sequence star. The protostar will contract and heat until the core temperature is sufficient for the strong nuclear force to dominate all interactions, basically between hydrogen and hydrogen nuclei. And so while a protostar looks like a star after its surrounding star has been blown away, it is not a star, right? So protostar, not yet a star. So not a star because it is still powered by gravitational contraction. All of the light or the photons that come out of the protostar, they are produced by just a push inward of the gravitational force. As the contraction continues, the core gets hotter and energy is released, and we say that is infrared and radio, and this is how we actually detect them. But at some point, if the hydrogen fusion starts, this is going to balance the energy radiated from the surface, and the contraction is halted. And we say the star now is born. The star has arrived on the main sequence, basically achieves a luminosity or brightness and temperature that are going to stay constant, unchanged, until all hydrogen in the core is used in the fusion process. So basically, all through the life of that star. How long it takes for a protostar to arrive at to the main sequence? It takes about 30 to 50 million years for a star like our own, and as we will see, it takes less for more massive star and more, so slower for less massive stars, than the sun. So now a few words about what happens during those birth stages. Say we start with cloud of gas. It's obviously on this x-axis of the HR diagram, right? We have the temperature, so hot in here, cold in here, very cold in here. You keep going. Okay, so the first stage is basically creation of the protostar. So somewhere here. By collapsing under gravity of that cloud of gas. And so as the protostar assembles from the collapsing cloud fragment, it is actually still concealed beneath this shroud of dusty gas. So it's a lot of dusty gas that enshrouds the protostar. Not observable, invisible wavelengths. All right. Okay. Now the protostar shrinks and heats up as the gravitational potential energy is converted into thermal energy. And we arrived at stage 2, where the surface temperature remains sort of constant. You see this kind of a vertical drop, so the temperature is not that much change. And it is in this phase that the convection is turns out to be the main energy transport mechanism within the star. But that changes in phase number 3, when the luminosity will stay fairly constant, while at these late stages of contraction is the radiation that is going to be leading the transport of energy through the star. And the surface temperature will rise. You see how it's moving horizontally. The temperature rises, okay, because the dominant mode of energy flow is now within the protostar. Okay, so the final one, stage number 4, the core temperature basically continues to rise until star arrives on the main sequence, basically achieves the required luminosity and temperature corresponding to a main sequence star. So the fusion rate is going to increase until it balances the energy radiated from the star's surface. You have it. And just a few notes. These life tracks, they're actually different for different masses. Now we have models that can be used to actually calculate. For example, for the sun, it takes about 30 million years to go from protostar to main sequence. So kind of like this. So to go through all these stages. So here would be proto-sun, somewhere here. It's going to take roughly 30 million years. However, for higher mass stars, so this would be these ones, much faster, okay, because the gravity is stronger, and so it overcomes all other impediments, all other forces that might it's going to be very difficult to balance all that gravity. So the gravity pushes, and the luminosity, the pressure and temperatures required for ignition of the fusion process happens much faster. While for the lower mass stars, look at them, right? About 150 million years might take for a much lower mass, say half the mass of the sun, so about 5 times slower. That lower mass star will be created, starting from the protostar phase to the star with the main that's going to be situated in, with quotes, on the main sequence, basically have those properties that we always see for stars on the main sequence.